Hello everyone, how are you? Are you able to hear me? Yes? Okay, good. We're on there. Double checking this thing. Yeah, great. Okay, let's go ahead and start. So, well, we're talking about Catalan numbers, and just as a reminder, there's an exam which is coming up on Friday. Something about the exam, I also want to mention, if you were doing the old exams, you may have noticed that some really, really old ones asked questions about expected value. That's actually not on the exam. People wondered what is on it. It's what we've covered about recursions and generating functions, and it'll go all the way through today's class where we finish up Catalan numbers. Okay, so let me go and switch to where I can draw, and I'm going to continue from where we left off last time. Just a second. I'm trying to figure out why. Oops, 1 second. The thing that I'm using here. Yes. Let me turn that filter on. Good. Okay, so here's where we were last time. And I want to bring us all onto the same page because this is a fairly complicated thing, which is actually quite easy in retrospect if you understand it. So bottom line was we said, okay, we want to know how many different arrangements can we make of these pairs of parentheses and pairs of parentheses. And we found out that it's hard to count them if you just count them. But instead, if you kind of look at, for the very first open, where does it close? You break into a lot of cases. And once you break into a lot of cases, you just see a pattern. And the pattern is the number of ways to finish with each of these is the number of ways to finish the part inside that first open and then close part times the number of ways to finish the stuff outside. This is all stuff we had last time. And that gave us a recursion, which was not a simple linear recursion. And in fact, it had different length for every different value of n. So then the game became, can we do anything with generating functions? And we found out that actually if you just square the generating function, you get something that looks a lot like that. And we ended up finding that the square of the generating function looks somehow just like the generating function again, minus the first term, but then divide by a z because we had to drop all the powers of z. And then that took us to the quadratic formula, where we found out that we have a formula for f of z. F of z is just equal to 1 minus the square root of this thing over 2z. But then the problem was we were too lazy to take any kinds of Taylor series. Instead, I mentioned at the end that there is actually something you can do with this Newton's generalized binomial theorem, which is that if I have anything of the form 1 plus something to any power, well, then you can write this down as some kind of a Taylor series, which may converge in some small window around 0. And it happens to look just like the binomial theorem. It's just the exponent choose stuff times the term to various powers of the stuff, adding forever. And it generalized the binomial theorem because if you had r being a non-negative integer, this would just stop. So now let's put everything together. All right? So the easiest way to remember this generalized binomial theorem is just do the binomial theorem with dots. That's really all that's going on here. And at some point they become 0, but yeah, that's just adding zeros. So back to the generating function, we have f of z equals 1 minus the square root of this 1 minus 4z all over 2z. I'm going to rewrite that on the next screen. Oh, yeah, after class, some people were chatting and asking questions. That was something separate. But f of z is equal to 1 minus, I'm going to write it as an exponential, like a fractional exponent. 1 minus 4z to the power 1/2 all over 2z. I think. Let me go back and double check. I think that's what we had. 1 minus the square root of 1 minus 4z. Yep, over 2z. Okay, so now if I want to do that, what should I do? I guess I should split this apart, and I should say there's one part of it which is going to be that Newton's binomial theorem piece, and there's also this like 1 and this 2z thing. The thing to think about is if you can just Taylor seriesize that part, it's great, because if you can Taylor seriesize that part, it's very easy to figure out how you put everything together to get the power series for the whole f of z. So let's now let's focus on what is this 1 minus 4z all to the power of 1/2. Okay, well now we know it's going to be a bunch of chooses, right? So this is just simply going to be, it's by the Newton's generalized binomial theorem, it'll be 1/2 choose 0 times negative 4z to the power 0. Let me do this, to the power 0. That's the first term. And the second term is plus 1/2 choose 1 times negative 4z to the 1 plus 1/2 choose 2, negative 4z to the 2, and so on. Is that clear? That's like what we just had with this Newton's generalized binomial theorem. We just took the power, choose, I guess, the term number, and then the thing which was the z is now the negative 4z raised to that power. I'm going to care about the nth term eventually, so let's think about what the nth term looks like. I don't know if I call it the nth term or not, but I'll just say it's like plus 1/2 choose n times minus 4z to the power n. Okay. Now for this, I'm not going to do my usual thing of doing n equals 7 and looking for a pattern. I'm actually going to go and hunt for the n because we will want to write down a bunch of dot dot dots. That's actually more convenient to do when you have the general term n. Oh yeah, and it keeps going, plus dot dot dot. Goes on forever. How could we possibly try to simplify this? Because I don't like how this looks. 1/2 choose n. I mean, actually, you could say this is the answer. You could say the answer to the nth Catalan number is, well, if I want the nth Catalan number, let's quickly check. Which term of this would I want for the nth Catalan number? I just want to make sure everyone's on the same page. And feel free to type raise hand in the chat. If I care about Cn, the Catalan number Cn, I'm asking this question because the answer is not the nth term here. How would I get the Cn? Braden.
You fill up the n plus first term because you're dividing by 2z, and so it would end up being 1/2 of n plus, or 1/2 choose n plus 1 times negative 4 to the n, or n plus 1.
Okay, so I heard this 1/2 coming out. Let's actually go and make that term, right? What Braden is saying is, look, if I want to get a Cnz to the n term inside this, it actually comes from the z to the power n plus 1 term in the rest of the stuff. With the exception of the z to the power 0 term, which might be weird, but let's worry about that separately. It's like, we know how to find the Catalan number for C0, C1, C2 by brute force. The interesting things are the big n's. And when I say the first one might be weird, it's just because there's a 1 minus here, and there's this extra 1. But in general, if I want to get the Cnz to the n term, the way it comes from is I get the z to the power n plus 1 term from the Newton binomial thing, and negate it, and I divide it by 2. Okay? So where that actually comes from is, maybe let's write the next row, just because that's the next one. It's plus this 1/2 choose n plus 1 minus 4z to the power n plus 1, and this particular term goes up into there. Is that clear? Like, this particular term has a z to the power n plus 1 in it, which is exactly what you need because you need to divide by this z in the denominator. And you might wonder, oh wait, is it going to be a legit power series? The reason it's going to be a legit power series, even though there's a 1 minus here, is because the very, very first term of the binomial theorem expansion is just a plain 1. So the 1 and the minus 1, this is 1 minus 1, they cancel each other out. And then that thing doesn't matter anymore. So I can actually divide by 2z. The reason I said that is because if for some weird reason the numerator of this expanded to have 5 plus something z squared plus whatever, you can't divide that by 2z, because what's 5 divided by 2z is not a power series. You can't take 5 divided by 2z. Does that make sense? So the important thing is that this 1 here, all that does is it knocks off this first thing right here. And that's it. So I'll use like some color here just to say that this 1 just knocks off this piece. And that's it. And then so the rest of the terms are just going to be simply this over, like negative this over 2z, all the way to negative this over 2z. And with that, we have a nice formula now. Now we know that the nth Catalan number, by equating the coefficients, that's just going to be minus 1/2 times 1/2 choose n plus 1 times negative 4 to the power n plus 1. I'm going to pause there because I want to make sure that this one makes sense. And also is correct, because I could make mistakes. Is this right? Well, this is the z to the power n plus 1 term. That's why I don't have a z to the n plus 1 here. And I have to divide by 2z. Then that's why there's a 2 here, and the z dropped to the power n. That's how it equated with that z to the power n. And there's a minus sign. So that's why there's a minus sign. Is everyone okay with this? We have now found the formula. That's the formula for the nth Catalan number. It's amazing. It's just take a negative half, like a half choose stuff. Okay, well, let's see if we can turn this into something more pretty, because we're not used to doing half choose. Okay, so I'm going to write that on the next screen. So Cn is equal to negative a half. That was a half, choose n plus 1, and then it was negative 4 to the power n plus 1, I think. Yes. All right. Any suggestions? How could I try to clean this up? If you were supposed to do a half choose n plus 1, I guess we could just do it. Well, what does that look like? What is 1 half choose n plus 1? Minus a half. What does that choose n plus 1 even mean? We can write down some stuff. We'll have some dot dot dots. The minus a half is just the thing in the front. Yes. Aaron.
Just do a half minus so if you say one is n factorial by n minus k factorial divided by k factorial. So it would be just like a half divided by half minus.
I'm just writing down what you said first. You said something like this. Is that right?
Yeah.
Yep.
So if you plug the numbers in, it'd be like a half factorial divided by n, like a half minus n plus n like minus half minus n factorial times like n plus 1 factorial.
I know what you're getting at. You're like, yeah, if I put those things into this thing with the half, I could expand this out and I could write it down. But the only problem is I don't have a good half factorial. So that was the thing that maybe I talked about too fast last time. I'm just going to swing back just so we remember where this came from. You see, the way we did this is we said, for these r's, even if the r is not a whole number, we could think of like r choose 3 to be that thing. And the reason is because it's not like we're just making stuff up. We're like, actually, we just want to do Taylor series. If you just simply do the Taylor series, you see that the coefficient of the z cubed is supposed to be that thing. R times r minus 1 times r minus 2 over 3 factorial, which we decided to generalize and say, we're just going to write that as r choose 3, even though r might be like half. Okay? So I'm going to use that as the lead off. What you said is okay. Actually, you can generalize what you said using something called the gamma function. If you define half factorial, what you said could be fine. But I'm just going to say, how might you try to write this out? I'm okay with dot dot dots. I'm looking for a pattern now. What could I do? Jack.
So I think, again, in that numerator that you're working on, the next one would be, I guess, minus 3 halves,
Yeah, okay.
and then 5 halves, and so on.
And how many of them?
I think n plus 1, or
Yep.
off by 1. I feel like it's n plus 1.
Yeah?
Okay.
Okay. And then you divide by?
N plus 1 factorial.
Good. And then you multiply by negative 4 to the power n plus 1. Now, let's clean this thing up. You see, now we actually have some stuff multiplied together. Could we potentially find some pattern? Oh, yes, if I'm going to multiply all the way to n plus 1 terms, maybe we can even write down what the last term is. That's ambitious. What is the last term? Can anyone help me with that? I always have trouble with that. What's the last term? I know that it'll be minus, and I know it'll be over 2. But what's on top? Does anyone know? I'm getting a ticking noise from the kitchen. Let me close the door. Sorry, my fridge was making some ticking noise. Okay, Andres says, is it 1 plus 2n? Is it? I mean, I'm asking you the question. I don't know. How many people like that? So you said 1 plus 2n. By the way, here's how I check anything like that. I check it in for a particular value of n. And in this case, I'm not going to do 7. 2n minus 1. Okay, well, we'll find out really soon, right? So I'm like, I know what I would do if n equals 3. If n equals 3, I see 4 of these things, right? If n equals 3, it should be going to the 4th one, because it's n plus 1. And if n equals 3, I would get, it's minus 1. That's how I see it's minus 1, right? Because I need to know that whatever I put in here actually matches what I would expect to see. So 2n minus 1. right? And that's because if it works for 3, it works for all of them. And if n is equal to 3, I want the first 4 terms. And then the fourth term, it would be 2 times 3, which is 6, minus 1 is 5, and that would be this one. Okay, so we wrote the whole thing down. So now we want to go and simplify. Can anyone have any ideas on how you could do some canceling or simplify? Do you see anything that's useful? By the way, do you know if any Catalan numbers are negative? Of course not. They're counting things. They can't be negative. So can we simplify? Yes, Nancy.
If you could, I guess, also negatives and also factor out the 1/2.
Good. So we're going to fix up all of the negatives and fix up all of the 1/2s. So the important thing is if you just look at it, there's clearly n plus 1 negatives. Sorry, there's n negatives here. One more negative there. That's n plus 1 negatives. And here's n plus 1 other negatives. N plus 1 plus n plus 1 is always an even number because I added a number to itself. So all the negatives cancel. Okay, that's the first important piece. So the important thing about this is that here you have n plus 1 negatives. And here you have n plus 1 negatives. And so whenever I have the same number of negatives and the same number of negatives, of course that will be an even number of negatives total. So it's an even number of negatives. Implies all signs cancel. Okay, that's convenient. So now I don't need to worry about negative numbers. You also want to fix the 2's. All right, is there anything I could do to kind of write down what's the power of 2? What's the way to do this? Well, I guess I'll do it since you suggested it already. So over here, how many 2's are in this part? So there's 4 to the power n plus 1. That is 2 to the power, twice as many of them. So that's 2 to the power 2n plus 2. Right? That's how many 2's we've got, because I had n plus 1 pairs of 2's. And now if I look at the rest of it, how many 2's do I have? I have n plus 2 2's, right? I have n plus 1 2's from these guys. And then I have another one. So I have n plus 2 2's. 2 to the power n plus 1, no, 2 to the power n plus 2 in the denominator. Okay, so what's the answer so far? Things got better. All of the negatives are gone. And I have on the positive side, I have a strange thing. I have like 1 times 3 times 5 times 7 times ... times 2n minus 1. On the denominator, I have n plus 1 factorial. And I have an extra times 2 to the power n. If I make a mistake, please correct me. I mean, I'm just like, this looks much prettier. I have a factorial, okay? I have this other thing. You may remember that I said that some people write this other thing as 2n minus 1 double factorial with 2 exclamation points. You could do that. But it turns out that this problem is much more beautiful than that. It turns out you can turn this thing into something that looks kind of like a choose. Because we don't really like the double factorial. Double factorial means you skip every other one, right? That's no fun. Let's just, for fun, multiply in something that will fill in all of those gaps. So what I mean by filling all those gaps is I'm now going to multiply by 1. I'm going to say that's equal to, I'm going to multiply by a blue thing, and the blue thing will be the same thing on the top and on the bottom. Can anyone suggest what would be good things to multiply on the top and the bottom? Nancy. Okay, so it is going to be an n factorial. That's what we're going to get. That's what we're going to get. I want to make a factorial on top, though. So what numbers are missing? Well, the even ones, okay? And that's where you're getting your factorial. So let's multiply in 2, 4, 6, and so on. And let's just go all the way to 2n. That's a nice even number. I'm going beyond. I mean, if I just was filling the gaps, I might go to 2n minus 2. But 2n's nicer to write. And on the denominator, just multiply by the same thing. I've simply multiplied by 1, so of course it's equal. Okay, good. Now, let's try to simplify this. This is true, so this becomes, the numerator is now a perfect factorial. It is a 2n whole thing factorial. The denominator has an n plus 1 factorial. I have this 2 to the n, and I still have the denominator. The denominator is still lying around. 2 times 4 times 6 times dot 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 times 2n. How do I rescue this denominator? It's really annoying. I have a 2, 4, 6. Whoa, I see a lot of raised hands all appeared at the same time. Nick, how about you?
Well, you can factor out each of the twos.
Ah, yes. So the thing is, we don't really like to do multiplying odd numbers together. I don't like to do odd numbers multiplied because that's not a factorial, right? But even numbers multiplied is a factorial. Actually, there's n of them. That's very convenient. I have a 2 to the n. I have n factors of 2 that I can use to cancel out every single one of those. So let's do it. The n cancels each of those into a 1, 2, 3, all the way to n. Oh my gosh, it's nice. It's just n factorial on the bottom. Okay, that was nice. So what is this? 2n factorial over n plus 1 factorial n factorial. Now that looks very convenient. That's like nice, right? This is like, how many ways are there to arrange n pairs of parentheses? Well, the number of ways to arrange n pairs of parentheses, which are legitimate, is 2n factorial over n plus 1 factorial times n factorial. Nice. And now I want to do a fun punchline. Let's compare that with a totally different question. So first of all, this is an answer, but I want to compare this answer with a different question. And the different question I'm going to ask is, how many ways to arrange n pairs of parentheses if you don't care if it's legit or not, of parentheses, if you don't care about valid. You know what I mean? I just mean I have n opens and n closes. And they can be like crazy. But it's going to be n opens and n closes. So, for example, now this thing is allowing things like close, 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 open, open, open. Okay. But it's n pairs of them. So I actually do need to have n opens and n closes. What's the answer to this question? This one doesn't need any generating functions or anything. Brayden.
Let's just do the choose n. So you can choose n spots for, say, the ones that are opening up to the right, and then put the left ones in the other spots.
Yeah, choose n spots out of the 2n spots for open. Why did I do that? So I just said that the number of ways to just like arrange any old parentheses is 2n choose n. And we were talking about how many of the ways are valid, right? So then we can ask this interesting question. What fraction of them are valid? Well, we know the number that are valid, the number valid is equal to the Catalan number, which I'll copy again from the last screen. That was 2n factorial over n plus 1 factorial n factorial. So what fraction of them are valid? Right? This is how many valid, that's how many total. And you should not expect a nice number. Who would have expected it would be a nice number? I wouldn't have. It's just like randomly being like, what's your chance of being lucky? Probably some crazy thing. Yes, exactly. It's saying you're right. It's just 1 over n plus 1. Because that's all there is. There's just an extra n plus 1. This actually is just 1 over n plus 1 times 2n choose n. So the fraction that are valid is just equal to 1 over n plus 1. Too nice. Does not deserve to be this nice, but it is. Okay, so that's the Catalan numbers, that's the formula. And actually, once you see this, it helps you double check if you were ever running into Catalan numbers again. It's like, well, it's going to be something nice compared to if I just was not thinking at all and typing some n opens and n closes. It's just 1 over n plus 1 fraction of them. All right, so that's the proof of Catalan numbers using this generating functions approach. I'm going to pause here and ask, are there any questions about what we just did here? Like, you know, we did this Taylor series thing. Sorry, go back. We did this like generating functions thing, found the generating function, did the Taylor series by using the Taylor series for Newton's binomial theorem, and then like hunted down what's the coefficient of the z to the n. And when we did that, we got a mess. and then we made the mess messier, and then somehow it all collapsed and became nice at the end. And that was the answer. If no questions, I'm going to go on, because I want to also talk about other ways to do this. So it turns out Catalan... Oh, question. What's this? Missed how we expand... Oh, yes. Let me go there. Thank you for asking. Okay. So what did we do here? So first of all, whenever I have a random real number, choose non-negative integer. What that means is, this is what happens here if I have like non-negative integer choosing non-negative integer. But if I have random old real number, you multiply together as many as many of the real number minus 1, real number minus 2, keep on minusing 1, do it as many times as that bottom number is, and divide it by the bottom number factorial. And the proof of why this worked was that's actually just what you did when you were doing Taylor series for the particular function, which is 1 plus z to the power r. That's what we did towards the end of the last class, where we just took all the derivatives of this, and as we took derivatives, we found that the r minus 1, the r minus 2, all multiplied out in front. And for Taylor series, you plug in the thing being 0, which is great, because 1 plus 0, I don't care to what power, that's going to be 1. Cool. So now I want to go on into another approach, and the other approach shows what Catalan numbers have to do with counting something very different. Okay? So what we're going to do now is we're going to ask a different question, which is how many mountain paths, I'm going to call them mountain paths, with 2n steps never go below the sea level. And I need to put an example of what in the world do I even mean. So what's a mountain walk? A mountain walk means that you're going to go diagonally. Everything is slope 1 or slope minus 1. And every walk takes a step which is the same size, like this. So what I'm doing here is that each step is the same length and has slope plus or minus 1. And the sea level is here, where you started. Okay. First of all, if I write this kind of question down, what do you see about what this has to do with what we have been thinking about? Yes, Sean.
It's like every up is in open parentheses.
Yes.
Down is in close parentheses.
Yes.
Not just close.
Yes. So it's just Cn. Is that okay? That's the nth Catalan number. Like, this is just a different way of looking at the same thing. All right? And if you see these things, these actually have names. They're not actually called mountain paths. You might see some other books might call them Dick paths, D-Y-C-K. Okay? And you might imagine these are kind of important. There are actually lots of applications of this. One application of this is called gambling. If you are gambling, and when you gamble, you can't gamble when you have zero money. Or if you, actually this is highly not recommended, but if you are speculating on cryptocurrency or something, but if you have like some money and you are investing it or something, if you've got positive money, you might get more money. And you might get more money, or you might get less money. But there's one problem about sea level. If you have no money left, you can't invest, supposedly, I think. I think that's how the thing usually works. So like this is often thought of as gamblers, which are going around gambling their money, and if you gamble and you do well, you can keep growing, but the moment you hit sea level, it's over. You ran out of money. Okay. Well, in their case, this sea level would be like 1 penny or something like that, the minimal unit of money. Because if you have 0, you can't do any betting. Okay. Now I want to count this in a totally different way. Of course, we know the answer is Cn. But once you write it in this way, you can turn your head 45 degrees, and you can ask it as a different question, which is how many, I'm going to call it up/right walks in, we're going to draw a grid. Here's a grid. It's going to have n, it's going to be width n and height n. And this grid is going to be something like, I'm just going to draw some of these things that are happening? Okay, I just did this. How many of this? Where you stay always above the main diagonal. In this, where you always stay above or on the main diagonal. Well, I mean, it's obvious this is the same question. Is that okay? Like, this is the same question. If I just made it n by n, all I did is, my thing is mirrored, so I have to look this way. But like, I have this thing flipped, and it's just the same picture. I have two n total things. I have n ups and n acrosses. And also, I need to kind of stay above this green thing, which is the same as staying above the sea level. So now let's just go count this, okay? I'm just going to count the grid thing, because the grid thing is easier for me to draw. Somehow human beings are much better at drawing grids than at trying to draw like 45-degree angles. I find it very hard to draw perfect 45-degree angles, but vertical is okay. And vertical and horizontal is okay. So now let's look at this particular thing we're counting. If I want to count how many are always above or on the main diagonal, well, the answer is how many are there where I don't care about this thing, minus how many there are where I go into the bad zone. Okay? So I'm going to say that the Cn is equal to the number of walks on, there's this n by n grid, this thing, number of walks on this, minus the number that go into the forbidden zone. And that was supposed to be a square, but I'm just going to do this, and I'm going to say the forbidden zone is here. Is that okay? My walks, by the way, my walks are always the walks are like up or right. Okay, those are my walks, up or right. If I allow myself to also go down or go back, the number of walks is infinite because I can just kind of go in circles. Okay? So I want this. Let's start. Which one is easier? Is there one of them that we can answer right away? Aha, Christopher.
That first term is 2n is actually like there's 2n steps and you choose n to either be up or right.
Yep. It's I've got 2n steps and I choose n of them to be up instructions. We saw this before. This is the problem we did before, walking on the grid. So I just need to do the other one. Well, how could that be easier? I mean, is it easier to count the ones that go into a forbidden zone? The answer turns out to be yes. And the reason the answer turns out to be yes is because you can use a technique which is hard to invent. It's called the reflection principle, which is what I want to share here. All right? So now let's think about the paths, the walks that hit the forbidden zone. Okay, if I have a walk that's going to hit the forbidden zone, let me draw a picture. It's going to look like this. There's this diagonal that goes across, and it's going to hit the forbidden zone. That actually means that if I drew the diagonal that's one underneath it, this thing here is exactly one underneath it, where, I mean, my scale on this is that this gap is 1, and this gap is 1. Forbidden zone means I actually hit the yellow thing, right? The only way you could enter the forbidden zone is you actually legitimately hit the yellow thing. Hit the yellow line. Is that observation clear? It's like if I want to count how many ways do I enter the forbidden zone, the moment you touch the yellow line, bang, you hit the forbidden zone. Let me draw one of these such paths. Maybe what happened is you kind of went up, and then maybe you kind of went across, and then maybe you went up. Let's make it simple for now. All the way up, and then across. Okay? By the way, you might hit the yellow line possibly multiple times. I'm just saying you hit it at least once. Now, it turns out that there's something you can do here, which the first time I ever saw it blew my mind, and then I had to remember it. There's something called the reflection principle. What if, for fun, for every one of these pictures, we drew another picture where we did some reflections? So we're going to associate it with, this is called a bijection, but it doesn't matter. I'm just saying for each one of these, I'm going to draw another picture. And the other picture happens to be the same. I'm going to draw the square, the yellow line, the green line, the yellow line. Remember, they are distances of 1. But now, what's going to happen is after the first moment when I hit the yellow line, because there is some time that I hit the yellow line, the first moment you hit the yellow line, the rest of it, we do a flip. We reflect the rest over the yellow line. So I'm going to draw exactly the same picture here. I went up, I went across, but now I hit the yellow line. And now, from now on, I just will flip everything across the yellow line. Does that make sense? I'm gonna reflect it across the yellow line, and just to contrast, maybe I'll use some, white color. So if I reflect across the yellow line, that's where the next thing is gonna hit. Okay, so it'll go like up, then across, and then it will go up. And what I've just done here is, from that first hit point thereafter, I reflected across the yellow line. From first hit of yellow line, and after, reflect the path over the yellow line. I want to give some time for this to digest, because this is a really amazing trick. Okay, so what exactly happened? I always will hit it because I'm counting the ones that hit the yellow line. And as soon as it hits, from there on after, you see what I did with this pinkish thing? It was doing that zigzag. And if you reflect that zigzag over the yellow line, then the zigzag ends up becoming the white thing. If it hit the yellow line many times, it's okay. I mean, here I hit the yellow line again, actually, as I was going past. But there's something interesting about where you end up. Do you notice how I was very careful to draw where I ended up? Where do you end up? I claim that no matter what you draw, if it's any pink thing which hits the yellow line, and you do blah, 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 and then you do the reflect, after the reflection, I claim you always end in the same place. And why is that? And where is that place anyway? And how would you know? Let's get some more people involved. So maybe Sean, what do you see?
It's the endpoint, but reflected over the yellow line.
Oh yeah, it's the old endpoint just reflected over the yellow line. That's the easiest way to say it, right? Because I'm doing something and I always go to the same correct endpoint, but now I'm saying in all of these that hit the yellow line, I'm going to reflect all of them over the yellow line. Well, then therefore they better all end at the place they're supposed to end at, reflected over the yellow line, which is exactly that one. That's why I was very, very careful to draw that one. That spot is exactly the image reflected over the yellow line of the supposed to be finish point, right? The supposed to be finish point was up there, and the yellow line is just coming right around. So I should be kind of like one down and one to the right of that, if that makes sense. Okay? So the important thing is that the end point is always the reflection of the correct endpoint over the yellow line, which is one down and one to the right. Of the correct endpoint. Okay? Great. So there's something interesting I drew here. You see, I drew a blue arrow that goes both ways. That's a very strong statement. Because so far I was just telling you, hey, if I take a bad pink line, which happens to touch the yellow line, which is what makes it bad, for every one of those, I can make one of these. Okay? But there's something interesting here. For every one of these on the left, I can make one of those on the right. But if somebody was just showing you the thing on the right, could you figure out where it came from? And how? The bidirectional arrow, so far we've only done one way. In a bijection, you need to say for everything here, there's something there. For everything here, there's something there, and so on. How come I have two arrows? If I have two arrows, then supposedly, if you never saw this in the first place, and you just saw that, you would be able to say, I know it came from this bad pink line. How would you undo it? Ah, Andrew. You reflect it again. Around where? So I'm looking at this guy, right? I've got this path. It happens to go from here. It happens to go to there. How did I know? How do I know not to reflect it there?
You would reflect it like across the yellow line, right? So were you saying not to reflect it?
Oh no, you're right. It is reflecting. I just want to be a bit precise on exactly what you said because it might cross the yellow line multiple times. How do I know which one to reflect at? Like, how do I know I don't just reflect that part? The first one. Yes, yes, yes. That's why the first was so important, right? Because we said the first hit of the yellow line. That's why I want to emphasize here. From the first hit of the yellow line, I should use the pink because that's what it was. From the first hit of the yellow line, that's where you reflect. So if you want to undo the reflection, you just go and find out that first place that you touched the yellow line. That's got to be where you did the reflection, right? Because whenever you reflect, yellow line's going to yellow line. And so you can't be like, after reflecting, magically I got another point on the yellow line. No, every point that was on the yellow line before reflection is also thereafter. Jyotia, you had something, were you going to say the same thing or do you have another question?
I was going to say basically.
Okay, good, good, good. So this is cool. So what we just found out is for every picture on the right that comes from a picture from the left, there's a unique way to get back the picture on the left. There's a unique, I'll call it reconstruction of the source from the left. You know exactly where it came from. And that is just reflect over first hit of yellow. Now, note that I emphasized this is true for every picture that came from the right. So what I'm saying is for everything I'm trying to count all of these things on the left. I don't know how many of them there are, but for every one of them, let's draw a picture on the right. And at least I know that the number of pictures on the left is the same as the number of these on the right that I could make from those. Does that make sense? It's like instead of counting these on the left, I want to count those on the right. And if I count how many of them there are here, well then it'll be if I count how many of them are on the right, I'll be good. But why is that good? How would you know on the right? Like, how would you know which of them could have come from here? Like what I'm talking about this bijection thing is that somehow I've shown that if I got something on the left and I try to make something on the right, I'll never double make. I'll never make the same thing twice. But then I need something that's called injectivity. I need something called surjectivity that will make my life really nice. In fact, I claim that everything that goes to here, everything that goes to this particular endpoint came from something over there. I claim that every single picture you draw, where you start from the starting point and you end at the reflected endpoint, I claim that every single one of those, I can point to a picture on the left, which is a bad path that touches yellow, that gave that picture. I'm going to write that down in words because that's important. But every path from the start to the reflected end. That's what we did. Reflected end actually has a bad path which is from the left that makes it. I'm actually saying that it's always, and why? Why is that? Chris? Okay, because if I run it through the function twice, I'll get the same thing. Because actually, if I find the place where it intersected, okay, it's over there. And then if I do another reflection around that intersection point, I get back to where I was. Yes. The only piece I want here is that there's one piece here called existence. How do I even know that if I start from here and I end at the reflected endpoint, how do I know I touched the yellow line? That's actually the beauty of it. That's why this proof is interesting. How do I know I touched the yellow line? Braden.
Well, I mean, if you like draw out the yellow line,
Yeah.
you can't go through the right. You have to like hover around and down and below the yellow line to get to the point.
Yeah, I'll call that it's obvious. There's no way you can get from there to there without crossing the yellow line. You just can't. So the amazing thing is that this new thing which we drew, every single path from the beginning to the reflected end, every one of those crosses the yellow line. Oh, that means I just find the first such crossing, reflect the rest. That'll give me a picture here. And that one is the unique one that partners with it. That's this huge observation, right? So the huge observation is, so the number of bad paths equals the number of paths that go from the start to the reflected end. This is huge. And so I want to pause to make sure this makes sense. It's like, before I don't know how to count, because it's like, how do you know, do you touch the yellow line or not? Too hard, I don't know what to subtract. And then over here, it's like, well, you know what? If you did the reflection, every single one of those bad things, it becomes one of these that goes from the beginning to this mysterious reflected endpoint. Okay, but it turns out that at that point, every single path that goes from the beginning to that reflected endpoint comes from one of those uniquely. So the answer is just how many paths from here to there. That's amazing. Actually, how many paths are there? Is that easy or hard? How do I know the number of paths going up and to the right that start from here and end there? Nick.
I think you can just fix going right twice, and then have basically the same thing. You're just on a line, on the diagonal line.
So we're on a grid, right? So you're like, you have to fix going right twice. So what you're saying is somehow before we had n ups and n rights. And you're like, not quite anymore. You have a different number of ups and rights, but we maybe can use similar ideas. I want to go and crystallize this a bit more. Jack?
Yeah, it looks like you have n plus 1 rights, am I right?
Yeah. So it's like,
2n total steps.
yeah.
So 2n choose n plus 1.
Yes. It's like I've got 2n total steps still, but now I have an extra to the right. So it's like I have n plus 1 to the rights and n minus 1 ups. So let's do this. Previous thing. Over here on the right-hand side, it is just the number of ways. This is equal to the number of ways to do n plus 1 ups and n plus 1 rights and n minus 1 ups. And that was equal to 2n, choose n minus 1 or n plus 1, whichever is your favorite. Bam! That's the formula. Subtract these two. That's it. So like that's amazing. No generating functions required at all. In fact, at this point, it's just algebra. What is that? If I want to subtract that, that's equal to 2n choose n minus 2n choose n minus 1. But we know the answer. The answer is supposed to be 1 over n plus 1 times this 2n choose n. So now let's just shape it into that answer. And the way we'll do that is we'll do some algebra. So this is equal to 2n choose n minus, let's write out this 2n choose n minus 1. It's 2n factorial all over n minus 1 factorial n plus 1 factorial. Now, if you wanted to turn the whole thing into 2n choose n's, I need to mess around with the second piece to make it look like 2n choose n. And the way I do that is I think I'll just multiply it by n over n. The reason is because I actually want to make an n factorial. In order to make it look like 2n choose n, I want to have an n factorial on the bottom and another n factorial on the bottom. And in particular, if I take this thing, I can rewrite it as 2n factorial over, there's a full n factorial now, and the n plus 1 factorial I can call n plus 1 times n factorial. Let's use green just to show that's where that came from. N plus 1 times n factorial, and there's still an extra n. Does it make sense what I've done? I just simply said, I don't like this funny form, I want 2n choose n. How do I force it to look like 2n choose n? Multiply by 1. And by multiplying by this particular n over n, I'm able to have an n to throw into my n minus 1 factorial. Why is this satisfying? I want to know the answer as a fraction of 2n choose n. What have I done? What is this? This is a certain fraction of 2n choose n. Sean?
This is n over n plus 1.
Yes, so I have a 2n choose n, and then I have a minus, it's simply n over n plus 1, 2n choose n. Oh my gosh, that's exactly what I wanted. Of course, math has to work, right? It can't be a different answer. 1 over n plus 1, 2n choose n. That's the nth Catalan number. Okay, so now we've just gotten like totally different way to solve this problem. One way to solve Catalan numbers was the generating functions, which is actually very satisfying. We even got this binomial theorem. The other way to get the Catalan numbers is to do this crazy reflection principle. And what you see on this screen here, this is just algebra. That's not the interesting part. I'm going to leave the reflection principle on the screen as we finish this class, because this is crazy. It's like, how would I count the stuff on the left? I don't know. It's just totally random stuff. But if you do that reflection, it turns out that your full set of what you're counting becomes a complete overlap. It becomes the same set as all the paths that start from there and end at the reflected endpoint. Because every single one of those happens to come from one of the original ones, and you'll never get the same one twice. Like, that's a miracle. It doesn't deserve to be true. That's actually the beauty of why this works. It's like, by doing this reflection, I'll never get the same thing twice, but oh my gosh, it turns out that the things that I'm getting instead, anything that you could possibly get by starting from here and ending there, well, it just so happens to be hit from one of those. So then the answer is just how many of those there are. And that's it. So that finishes all of our recursions, generating functions, Catalan numbers, and that finishes the unit. If people have any questions, I'm happy to answer them. I'm just going to stop the broadcast on